Hello everyone, welcome back to this online class. Today we are going to look at Newton's backward difference interpolation technique. We are given this question. We are asked to discuss the Newton's backward difference interpolation technique and hence work out the following questions. So the question is that the profits in $1,000 of a certain company between the year 2002 and 2014 are given in the table below. So we have the table for the year and the profit. We have to use Newton's backward difference interpolating polynomial to determine the profit in the year 2012. So first of all, we are going to derive the formula for the backward interpolation, and then we use it to answer that question. So again, take note that this is only used when the x values must be uniformly spaced. X values are the tabular values. So in our table, we are going to say let the year denote X and let the profit denote f of X. So look at the spacing from 202 to 205, that's 3 years, 205 to 208, 3 years. So the spacing is uniform, that is 3 years. Now, I want us to recall the backward difference operator. You can write recall that the backward difference operating on Fi is the same as Fi minus Fi minus 1. In terms of the shift operator, this is the same as identity operating on Fi minus the shift raised to negative 1 operating on Fi, which you can write as identity minus the shift raised to negative 1 operating on Fi. And so this will cancel. Therefore, the backward difference is the same as identity minus the shift operating, the shift raised to negative 1. I want to make E, the shift operator, the subject. So when you make E the subject, so this means that our shift operator is the same as identity. Remember, identity is the same as 1. You can take note that identity is just the same as 1. So I'll just replace it by 1. So it will be 1 minus the backward difference. This is raised to negative 1. So now we know the shift operator in terms of the backward difference operator. Now, you know the interpolating polynomial is given by Pn of x. So you can write interpolating polynomial is, we are saying Pn of x is approximately equal to f of x. It is the polynomial used to approximate the function, the unknown function, f of x. And you also know that there is a transformation that we have to make here, that s is equals to x minus x naught over h. So you can write, use the transformation s is equals to x minus x naught over h. So from here, you're going to get x is equals to x naught plus s h. This transformation will transform the tabular points, that means the x values, to integers. We already demonstrated this when you are looking at the forward difference technique. So let's substitute x into the interpolating polynomial so that you're going to get this. You say therefore, let me write it this side. You can write Pn, instead of x, we'll write x naught plus sh is approximately equal to f of x naught plus sh. Remember, x naught plus sh is the same as x subscript s. So this equals to, I can write it down here. This equals to f subscript, f of x subscript s, which you can write as f subscript s. So now let's express f subscript s in terms of the shift operator. So you can say, but fs is equals to the shift raised to s operating on f naught. Our shift is the same as, we got it here, it was 1 minus del the backward difference raised to -1. That's the shift operator. This is now raised to s, f naught, which you can as well write as 1 minus delta raised to -s operating on f naught. So let's expand 1 minus delta raised to -s. I want us to recall that you can write a note. A plus b raised to n is equals to n combination 0, a raised to n, b raised to 0, plus n combination 1, a raised to n minus 1, b raised to 1, plus n combination 2, a raised to n minus 2, b squared, plus so many other terms up to the last one, n combination n, a raised to 0, b raised to, that is binomial expansion. So I need to substitute. You put, where there is a, I'm going to substitute 1. Where there is b, I'm going to substitute negative delta. And where there is n, we are going to replace that by negative s. So this can now be written as, it can now be written as, so let me write it this side. It is equals to, that is negative s combination 0, then the second term is now negative s combination 1. So when you work it out, this is what you need to get. This should give you 1 plus negative s times negative delta, that should be negative delta, plus negative s minus 1 over 2 factorial negative delta squared. Somebody's wondering where I'm getting those. So you see, when you work out this, you are going to get, let me say this one should give you, of course, n combination 0 is 1, so it is 1 times a raised to n plus n a raised to n minus 1 b plus n minus 1 over 2 factorial a raised to n minus 2 b squared plus so many other terms up to the last one b raised to n. That's what it means. So that's what I'm replacing. Where there is a, you put 1, b is negative delta, and n is negative s. So that this is what we get. Then plus negative s minus 1, negative s minus 2 over 3 factorial, negative delta cubed, plus so many other terms up to the other one is plus s plus n minus 1 combination n delta raised to n plus the last term is delta raised to s operating on f naught. So this can as well be written as, if I open the bracket, I'll have f naught plus s backward of f naught. Here we'll have plus s plus 1 over 2 factorial delta squared f naught plus s plus 1 s plus 2 over 3 factorial delta cubed f naught plus so many other terms plus s plus n minus 1 combination n delta raised to n operating on f naught plus so many other terms up to delta raised to s operating on f naught. So that's what we have. So now we truncate the series after the term involving the nth order. So you can write here, truncate this series after the term in delta raised to n to get the interpolating polynomial as, so what I mean is this one. When I consider from this term, the first term, all the way up to the nth order term, up to here, that will give me the interpolating polynomial. So anything going onwards will be the truncation error. So we are going to get our polynomial as p, because it's a polynomial of degree n, so that is pn of x. And remember, x is x naught plus sh. So pn of x is equals to f naught plus s backward of f naught plus s plus 1 over 2 factorial, the second order backward of f naught plus s plus 1, s plus 2 over 3 factorial, third order of f naught plus so many other terms up to the last one is s plus n minus 1 combination n backward nth order backward operating on f naught. So this is our polynomial that is used to approximate f of x. So let me bracket this polynomial and comment on it. You see, this is a polynomial of degree n in the new variable s, and even in the backward difference operator. So this polynomial is called the Newton's backward difference interpolating polynomial. This is abbreviated as Newton backward difference interpolating polynomial, the abbreviation. It is a polynomial of degree n. Now, you see, this polynomial will give you the approximate value. It's not the exact value, but the approximate value. So there's an error due to truncation. So how do we find the truncation error? So the truncation error is, look at where we've truncated. We've truncated from n plus 1, combination n plus 1 going onwards. So what we'll have here, now it means where there is n in this last term, we substitute n plus 1. So we'll have s plus n, combination n plus 1, delta raised to n plus 1 operating on f naught. That will be our error. So the error E, that the truncation error, is approximately equal to s plus n, combination n plus 1, the backward difference raised to n plus 1, of course the n plus 1th order backward difference of f naught. And this can as well be written as s plus n, combination n plus 1. Now we replace that backward difference by h raised to n plus 1. Then f n plus 1. N plus 1 there means the derivative of that function at x naught. That's what we have as the error. So there's something you need to take note of in this polynomial. So there's a note NB that in this note that the Newton backward difference interpolating polynomial is used when the tabular points is used when the tabular points, that means the x values, those are the ones you're calling tabular points, are uniformly spaced. Uniformly spaced. And something that you also need to take note of, that it is used to estimate values. It is used to estimate values of f of x at non-tabulated points, which are close to the end of the table. To the end of the table. So the key term here is the end of the table. Why end of the table? Is because look at how we were reading the backward differences along a line that was sloping. We are reading them along a line that was sloping upward. And so that's why we need to predict only values that are very close to the end of the table. I will explain that in the example. So we have derived the formula for Newton backward difference interpolating polynomial. Now let's answer the question. Look at our table. Let me take you back to our table. We are given the year versus profit, and we said let the year be X and let the profit be F of X. So for us to be able to get the profit during the year of 2012, we first of all need to come up with a finite difference table for this data. So let's construct the table. Of course, finite. There's a difference between the table of data which have been given and the finite difference table which we are yet to construct. So now we say work out the question. Work out the question. So what we do here is to construct the finite difference table. Finite difference table. So we need X values and the F of X values. Of course, we will have here the year, that is X, and profit, that will be F of X. Horizontal line, a vertical line. So let's populate those values of X and F of X in this table. So we have written the X values and the F of X values. Now let's get the first order backward differences. So you write a backward difference operating on F. As usual, we subtract 100 minus 120, that is a negative 20. 111 minus 100, that is 11. 108 minus 111, that's negative 3. 99 minus 108 is negative 9. So do the same to the second order backward differences. So again, you subtract 11 minus negative 20, that should give us 31. Write it here. Negative 3 minus 11 is negative 14. And negative 9 minus negative 3 is negative 6. Go to third order. Negative 14 minus 31 is negative 45. So let me use this color. Negative 6 minus negative 14, that is 8. And lastly, the fourth order differences, that should be fourth order, not third. So that is raised to 4, operating on F. When you subtract, you're going to get 53. So that's the difference table. Let me wrap this line, is too big. Up to somewhere there. That's fine. So now we need to predict the profit when the year is 2012. 2012 is somewhere here. But first of all, let me explain something about this difference table. You see, we have done the subtractions up to our last value is in the fourth order column. So it means our interpolating polynomial must be of degree 4. Because the last column is the fourth order column. So you can say since the last column is 4, comma, the interpolating polynomial must be of degree 4. So we call it P subscript 4 of x. That will be F naught plus S backward of F naught plus S plus 1 over 2 factorial, second backward difference of F naught plus S plus 1, S plus 2 over 3 factorial. Let me take this to the left. So this will be third order backward difference of F naught. Then lastly, we'll have S plus 1, S plus 2, S plus 3. This should now be over 4 factorial. Remember, this is S. Then there is the fourth order backward difference of F naught. So delta raised to 4 of F naught. That is our polynomial. So what is S? So look at we need to predict or simply estimate F of 2012. That's the profit when the year is 2012. So this one is our X. So you're going to say let X be equal to 2012. Let's go back to the table and locate it. 2012 is somewhere here. 2012. I want to know the value when X is 2012. So because of backward, now we choose X not to be any value of X which is just below 2012 in the table. Why is it below? Because we are going to be reading along a line that is sloping upwards. Remember, for the forward difference, you are choosing a value that was above. In this case, because of backward, it must be a value that is below X in the table. So automatically that will be 2014. Our X naught will be 2014 and our X is 2012. So X naught here is 2014. What do you think is H? Look at the spacing between the X values. That will be 3. The spacing, I can comment here that H is the spacing between the X values. And you see it is uniform. This is the spacing between the X values. It is uniform. That spacing must be uniform. If it is not uniform, then you cannot use this formula. So with this, we can now be able to get our transformation. So this implies that our S is equals to X minus X naught over H. That is 2012 minus 2014. Our H is 3. That is negative 2 over 3. So that's our new variable, which now transform the X values to integer. So S is negative 2 over 3. So we know it. What else do we need? We know F naught. We can get it from the table. We can also get delta backward of F naught. Second order backward difference of F naught can get from the table. Third order backward difference of F naught read from the table. And lastly, fourth order backward difference of F naught you can also read from the table. So let me show you how to get them. Go back to your table. Because this is our X naught 2014, that's our X naught in this case, then it means that this one will be our F naught. So you need to read along a line that is sloping upward. This is the line. From F naught, we read in this direction. Those are the values that we are interested in. So this value here, that is the same as backward of F naught. This other value is the second order backward of F naught. So backward squared F naught. This one is backward cubed, or simply third order backward of F naught. Backward cubed of F naught. And lastly, this one is the fourth order backward difference of F naught. So we have them now, we can replace in our polynomial. And we also know F naught and we know S. So therefore, when we replace back, this is what you're going to get. Go back to the polynomial. So you can say that therefore, F of 2012 is approximately equal to P4 of 2012. And that is equals to F naught, which is, in this case, it was 99. Then plus S, which is negative 2 over 3, times the backward of F naught, that is negative 9 from our table. So you just read the values from the table. So the other term is plus S, which is negative 2 over 3, S plus 1, negative 2 over 3 plus 1 over 2 factorial times the delta squared, that was 8, plus the other term is S negative 2 over 3, negative 2 over 3 plus 1, negative 2 over 3 plus 2, this should be over 3 factorial, delta cubed, let's see, delta squared was 6, so let me just change this, should be 6, not 8. Delta squared was 6, just a correction. This negative 6. And this other one is 8, delta cubed, operating on F naught. And finally, the other term is negative 2 over 3, that is S. S plus 1, so that is a negative 2 over 3 plus 1. Then we have S plus 2. I'll take this here. Negative 2 over 3 plus 2. S plus 3 is negative 2 over 3 plus 3. This should be over 4 factorial. Then delta raised to 4, operating on F naught, we got 53. So right here, 53. So you are going to press the whole of this in a calculator so that you get 103.7449. Remember, it is in $1,000. $1,000. So you can say therefore, you can just conclude and say that therefore, the profit, let me use another color. So you can say therefore the profit in the year 2012 was 103.7449 thousand dollars. $1,000. So that's how to use backward difference to be able to obtain the approximate values of f of x. And you see, you can approximate this 1.03, 103.7 is the same as, of course, 104 when you round off to the nearest whole number. So thank you all for watching this video. Please subscribe to my YouTube channel. That is Professor Francis Okech. When you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, like, and share this video. When we meet next time, we look at more problems involving backward difference interpolation technique. Bye-bye.